Very good morning, all. Welcome back to the class. And I'm sure now you are in a better position to understand the discussions about the last logic, which we talked of Huffman coding. So last time we have already discussed many issues related to Huffman coding, and I asked you to implement using certain new concepts. I'm sure you have attempted that, and now I'll show you some sample code which will help you in understanding the things in a better way. If you have already attempted some coding, you might have faced certain problems. So I implement here Huffman coding using the node structure. And as I discussed last time, that union can be useful. So I'm storing the frequency, the flag being used to differentiate whether union is being used correspondingly for the movie name or correspondingly for the left and right pointers. Then the movie name can be one particular field of the union, and other field can be left and right, both pointers as a group. So I'm taking this as an inner node versus leaf node. So that will be the corresponding change for the structure. As I said earlier, that taking an array of pointers as a heap or priority queue will be a useful implementation, and root pointer to be returned by Huffman tree. So that can be another good option to return. So I'm using in the main this, and then code which we will be generating as a global maybe, but you can definitely take as a parameter also. So here, the first thing why I'm using array of pointers, effectively, I'm creating here each node which I'm reading to be initially directly put into the heap. And then I will make the build heap. So I am creating each movie name as a malloc, etc. Within that, the movie name and frequency being read. And initially, I'm creating flag as 0, meaning that currently movie name is used, pointers are not used. Later flag will be updated as per requirement. Then I make the corresponding build heap Huffman tree, and then Huffman tree call will be returning the root, and code will be generated, and that will be displaying the code. So build Huffman tree is my main logic. Now, in this case, of course, I will start with making the build min heap. This function you have already written, and the same code can be reused, except that the type of the variable will be now struct array pointer, and earlier it was a normal array of integers or array of structures. But why I'm doing this now, it will be more clear that my extract min will return a pointer to the structure. X is a pointer. So just see that I will make my extract min function correspondingly to return. So like I have build min heap, so extract min also I have here available. I'll just show. Extract min will have a return of pointer to the structure. Pointer to the node will be returned, and that pointer returned will be now useful. Why pointer? Because if you take X as a local variable and you store some data returned into X, then if you make left to point to ampersand of X, it will actually fail in the later stages because X will be a local variable, and once function is over, X will get destroyed, and that pointer which you stored in left or right, like this one. So if you store here a pointer to some local variable X, that will become later a non-existing pointer and called as a dangling reference. I hope you can understand what I am discussing, but if not clear, still you can understand that X here is storing the pointer only to the extracted variable, and extracted variable was actually done malloc, so that variable exists permanently and is connectable to left and right side. Rest code is simple. I created a new node, flag becoming 1, that it is becoming internal node, frequency updated, left and right pointers updated. For accessing the corresponding pointers, the syntax will be accordingly correct. And this tells that union is being used for which purpose. So accordingly, this done, and now new node will be inserted, and I will be repeating this process n-1 times. And once I'm ready, the corresponding root is ready via extract min. That is the only value remaining on the top of the heap, and that will be returned via this particular logic. So this will become the correspondingly function. Rest all remaining similar. What you have already done: build heap, insert, etc. Extract min, all decrease key, etc. If you needed min heapify, whatever used, the same code can be used. Then comes generate code. So in generate code, the Huffman tree root is passed, the code which I want to generate, if I want to have it as a parameter, I can have there. And then correspondingly up to which level I have reached, K will be recursively used. So initially, if I say, if I am on the leaf node, the result is ready, code is ready, effectively the movie name, frequency name to be printed, and the code to be printed. If I want to store the code, then this line can be used. In the corresponding structure, I should have the code stored, and then I can have that. But if I'm not, then I'm directly printing. Otherwise, I will initially have left side traversal. Left side code is 0 followed by the code generated for the left subtree with value k plus 1 as the next depth, and then followed by the same code being started with 1 followed by code for the remaining subtree, which will be from k plus 1 depth onward. So this way you can easily do that. Rest code is simple. So I think this much code is sufficient to discuss. And I'm sure with this, you will get the clarity of why we are using this. So in this case, we have used array of pointers. Of course, array of structures also could have been one alternate. So alternate one, which we have used, was array of pointers for a heap to structure. So my PQ oblique heap was implemented using this. Alternate 2 can be, of course, that instead of array of pointers, you can use array of a struct directly. If you use array of a struct, that will mean effectively you have not pointers stored, but the only change in this case needed is whenever you have a left node to be given some value, then you have to do every time a new malloc to this, because left is guaranteedly a pointer. So you have to first create a malloc, and then whatever extract min data you extracted. So extract min data, let's say you got in X, then effectively you have to copy X and similarly Y also into the malloc or memory allocated to left and right. So whatever X data is, the full data is to be copied here from X. So it is one and the same thing. Either you do this, every time this copying will be needed, and every time whenever you do extraction, that time you have to do this process of malloc, and then every time this copying of the data. So that process, if you follow, it will be needed always. Left as well as right, in both directions, these things will be needed. And this process can be another alternate. But by the code I have shown, now you are clear probably this. Well, after this, now we start with the next discussions. So today we are going to discuss something about chess game. Chess game, I'm sure many of you have played, but probably most of you are aware of that. In fact, chess game is one which is said to be a very intelligent game, and the most powerful piece in this case in the chess, as you all know, is your queen. So the queen is so powerful because queen can have movement in many directions. It can go vertically up to any number of cells. Any number of cells can be gone up vertically or vertically down anywhere. Left side horizontally, right side horizontally, any number of cells. Diagonal, either downwards or upward, and the other diagonal also. So it has all possible, effectively 8 possible moves. 1, 2, 3, 4, 5, 6, 7, 8. 8 possible moves, and in any up to any cell, one or more number of cells can be moved. So what the problem we are supposed to solve is that we have n queens, let's say. So it's called as an n queen problem, which says that you have n into n chess boards, and aim is place n queens on this board in a way such that no queen attacks other. So if you are able to implement that, I think that will be, I'll just shift this. So no queen attacks others. That is what, if I am able to implement, this is what we really want to achieve. So this is what is my n queen problem. Obviously, now let's take an example and we will be able to understand it. Let's assume n equal to 4. So I mean there is a 4 into 4 chessboard. 4 into 4 chessboard, 4 queens to be placed. Now, 4 queens to be placed, what can be the solution? Obviously, I have to make the placing. So one thing is clear, each row can have one and exactly one queen. That is first and foremost thing. Because n queens are there and n rows are there. Row-wise attack definitely happens. So within one row, I can't have more than one queen. So I can guaranteedly say each row will have one and exactly one queen. Now, my problem becomes simple. So I have 4 rows and I want to find out one queen to be placed in each row at some place, at some position, such that attack doesn't happen among them at all. For example, if I have this as a chessboard, then I say, fine, I will place queen Q1 first row, queen Q2 in second row, queen Q3 in third row, and Q4 in fourth. So that part becomes simple. Now, I will say where I can put. The logic, if you have to do systematically, if you are not very smart player of the chess, maybe you will say, okay, I'll explore different positions and find out how to solve. And whatever way we logically work will be a direct implementation correspondingly for the implementation needed of the logic development via the algo which we are going to discuss. So I'll say, fine. First thing, obviously, I will start placing Q1 here. I place Q1 here. Then, obviously, the second queen, I have to think of where to place. So I will say, place here. I will say, this is rejected because it will be having an attack. Then try here. Again, you will say reject. Then you will say, okay, I can place Q2 here. Accept it. Now Q2 is placed. The target will be place Q3 somewhere. I'll say, okay, this can't be placed, rejected. This attack diagonal is there, rejected. I will say, fine, place here. Then after placing, I'll find this is also having an attack, rejected. Place queen Q3 here. I'll find, okay, if I tried, then it will be rejected. So this also gets rejected. And Q3 cannot be placed anywhere. As soon as I find that Q3 cannot be placed, I guaranteedly say that I'm going in a wrong track. Answer is not possible. Answer in this direction is not possible. Answer is not possible. That means I have to probably go back and revert with some other attempt. And this is what is called as a backtracking. So I backtrack, I go back and say, no, whatever I am doing, probably I am proceeding in the wrong direction. So I'll say, fine, Q1 was here. I have already attempted Q2 placed here, but then I am not able to find Q3 at all. That will mean backtrack and say, no, Q2 should not be placed here. I will say, okay, don't place Q2 here. Let's place Q2 here, Q2. So Q2 in the second row comes placed here. And then once placed here, I will say, okay, try for Q3 now. Again, try for Q3. I'll try here. Not possible. Try here. Yes. Q3 can come here. Accepted. So Q3 ready. Then I'll say try for Q4. So I proceed. If I have already found for previous level, next Q I try. Can I place here? No, I tried and find and rejected. Here also I will try and reject. Here also I will try and reject. Here also I try and reject. So I said now that means Q4 not possible. That means no solution for Q3 possible. Go back to Q3 and backtrack and try Q3 somewhere else. So don't place Q3 here. Can I place Q3 here? No, there is an attack. Can I place Q3 here? No, no possibility for Q3 also. Q3 rejected. Rejected mean again go back. Try for Q2. Q2 further cannot be. So tried for another Q2. Q2 again rejected. Rejected will mean I have to go back again, backtrack to Q1. And if I backtrack to Q1, I will say Q1's this position is not acceptable. So that means I have to try with some other value for Q1. So don't put Q1 here. Let's try to put Q1 here. If I put Q1 here, then I will try for Q2 to be placed. Can I place Q2 here? No, rejected. Can I place Q2 here? No, rejected. Can I place Q2 here? No, rejected. I can place Q2 here. Q2 fine. Then I will say go for Q3. Can I place Q3 here? Yes, probably this is not under attack. So Q3, one possible place can be this. If accepted, fine. Otherwise, I will explore further. Q3 placed here. Then I will say Q3 is ready for the time being. If ready, then try for Q4. If ready, then go to the next level. Otherwise, backtrack. Q4 I reached. Can I place here? No. Can I place here? No. Can I place here? Yes. Q4 found. So I have found Q1, Q2, Q3, 4 solution ready, and I can say answer is prepared. Had it not been there, Q4 will be next attempted. If rejected, again Q3 will be next backtracked and explored and like that. Yes, dear friends, this is precisely what is called as a backtracking strategy. So this is one of the fantastic strategy which works excellently. And this methodology is fourth strategy of the discussions which we have already done. So earlier we have done divide and conquer. Then we followed that with the DP. Then we went to greedy. And then now we come to the fourth strategy, which we call as a backtracking. So effectively backtracking, we have already seen that we are going to use certain permutations. And we are going to explore permutations. Whenever I find that they are not possible to further progress, I am going to reject. But what I did, like in n queen problem, what I started, I said for queen Q1, I have 4 choices. Say n was 4. So I said for 4 queen problem, I said Q1 can be placed at 1 position. Q1 can be placed at position 2. Q1 can be placed at position 3 and at position 4. But position 1 meant that within this, I have this 1, 2, 3. So this is position 1, this is position 2, position 3, and position 4. If I placed Q1 here, further I had 4 choices for Q2. Q2 can be placed at 1, at 2, at 3, at 4. I said no. This I tried and then I said reject. Because it is going to attack, so this will be rejected. I will backtrack and go to the second solution. Here I will say, can I place within the second place? Second queen, again rejected. Backtrack. Try at a third place, accepted. Accepted means explore further. Further explore means, again for Q3, I have choice of queen at third being placed at position 1, 2, 3, and 4. So my queen 1 is here, queen 2 is here. Then I start exploring for Q3. Now I will explore this and say reject. I will say explore this, reject. Explore this, reject. Explore this, reject. This means this further rejected, go back and go in this direction and like that. So if you say somewhere it got accepted, that will mean 4 choices for Q4 also. Q4 to be 1, 2, 3, 4, and then according. So if you see total permutations, how many permutations I could have if they were not rejected initially. Say for 4 into 4, initially I had 4 choices for the Q1, followed by for each of them another choices for Q2, then followed by another 4 choices for each of them for Q3, and another 4 choices for each of them for Q4. Effectively, this means 4 raised to 4 choices. Effectively, more or less, it becomes n raised to n choices. Of course, that means exponential growth. But there will be certain problems where you need all permutations. Some problems will need such situations. And then there is no choice, but you have to explore all them. They will need all permutations to be attempted. Then there is no choice, you need a standard algorithm. For example, I say find power set of a set. Now, power set of a set, I know this has exponential number of elements if power set of a set of n elements is to be found. Now, if there is a power set to be found, obviously it is going to have all exponential. So I have to find out. So backtracking method is effectively a systematic method, and it's a systematic approach. But systematic approach in a way that we need not explore every permutation if we are not going towards the right answer. If in between I find that answer is not going to be achieved on this permutation, we will reject that. So what effectively we have done here is, let's say I say that for 4 queen problem, I want an answer to be generated as an array X 1 to 4 in a way that X1 will tell the position for queen 1, and that is obviously in row 1. So I want X1. Similarly, X2, I want position for queen 2 in row 2, obviously. So row is implied, queen number directly tells. So in general, I say Xi is position for queen number I. And I want to generate that. So what I want is, for example, my X array corresponding to 4 queen solution, one answer can be that queen 2 is placed at position 2. Like in the last page, we found that Q2 queen at position. I found my answer to be correct in this particular chessboard as this. So Q1 was placed here, followed by Q2 placed here. Then I had Q3 placed here, and then I had Q4 placed here. This is position 2 in row 1. So I say this is X1. This is position 4. So I'll say Q2 to be position 4, Q3 to be position 1, and Q4 to be position 3. This is nothing but position of queen 1, position of queen 2, this is queen 3, this is queen 4. So this is precisely my solution. So I say my final answer is nothing but it's a vector of n elements. But how it is being generated? I am generating it incrementally. That's the beauty of the algorithm. And that's how backtracking will be automatically working in this case, incrementally generated. So my logic says that what I am going to generate is effectively, I will generate one component at a time and proceed to explore further. So what I generated, I said, let x1 be generated. And obviously, initially x1 is okay. Then I will generate some value for x2 and check. If acceptable, then I will say use these values, and x1, x2 are already okay. Give another increment, generate x3. If acceptable, then again increment and generate x4. x2, x3 is already ready, x4. So every time I will increment one new value and explore. If not acceptable, means backtrack. Backtrack will mean initially current value of x4 not acceptable, try next value. Next. If nothing acceptable, means backtrack and try with next value for x3. If x3 also not acceptable, try with next value of x2. x2 also not acceptable, try with next value of x1. So this way, acceptable will mean go to the next step. So every time I have a simple logic that acceptable up to xi. So I have x1 to xi solution partially ready, will mean xi plus 1 to be explored for higher solution. But if not acceptable will effectively mean that current value of xi is not acceptable, next value of xi to be attempted. If no value exists, then nothing but backtrack and you treat the solution available for x1 to xi minus 1 and explore remaining values of xi minus 1. So we have many possibilities for xi minus 1 also, and we will be exploring possible values of that particular one. If not acceptable, still backtrack. -2 and so and so. So this is what is going to be my logic correspondingly to this particular situation. Now, having said that, this becomes the simplest way. Of course, I can see that all n raised to n permutations explored. Obviously, that will mean more time complexity or exponential time complexity effectively, but we don't have a choice. Exponential have to be done because we need all exponential or all permutations them. But good part is that we are not going up to the depth every time, not going up to the leaf node every time. So in between, we are rejecting whenever needed. So that probably will save some time for us. Now, having said that, if I try to implement, so I will say, let's talk of implementation. So for answer, I will say, I will take X array 1 to n, and X1 will be assigned some value for queen 1, and then explore further. Explore for acceptance and further solution. Acceptance and like that. So my solution will be incrementally built. X1 will be initially built, then I will make another answer for X2 and slowly like that. In this case, in order to have backtracking working without any extra logic or coding to be done, the beauty of the algorithm becomes that we will have mainly two modules. Module 1, which will be having general backtracking logic. And automatically, all backtracking possibilities should get explored. So all possible answers, all possible values for every xi and further or previous level to be explored. That will be a general backtracking module. And the second module will be the problem-specific checks. What does that mean? It will be more clear when I just say that at any time I'm saying x1 to xi to be checked, whether acceptable or not, for acceptability or not, whether it is going towards a possible correct direction or not, for correctness. So till now it is correct or not. How to check correctness? Whether current queens are attacking each other or not. So that part I call as a bounding function. So bounding function is a problem specific and it tells whether attack happens or not. Attack of queens in this case. Some other problem. So this problem, it will be checking the attack of the queens. Some other problem, similar other logic will be there. So every time I will say whether x1 to xi solution is acceptable or not. Assuming that up to this solution ready, if correct, go ahead. Otherwise, backtrack. Now knowing this, my coding becomes very simple. What will be the coding? I'll say I need one n queen function to be written, which is a general function. And I will need one more function, which will be the bounding logic. So n queen function, how to implement? Of course, n definitely I will need. And as you can smell, it will be a recursive function. So I will be at a time attempting for one queen, starting with 1, then 2, and then going on. So I say at a time I will be trying for some queen k, means that initial call will come with 1n. So k will be initially 1 and I'm going to find that. What I want is, I want to find out where to place kth queen. The kth queen is to be placed and we have to find the place for this. Effectively means I have to find xk to be something. That is what is my logic. And of course, along with backtracking or further recursive calls to be implemented. So this plus next recursion to next level. Or if not possible, then backtrack. So this is what logic I want in this module. So how to do? I want kth queen to be placed. What are the possible answers for kth queen? Say first queen, where it can be placed. What are all possible values? Yes, you are right. All possible values are 1 to n. Queen first or any queen can be placed at position 1 and up to n. I'll take some variable xk variable without array subscript I'm using. So this means whether xk is acceptable or not, I will try. And if it is acceptable, I will store it into array x. Otherwise, I will say it is the value being attempted. Now, for xk means current queen can be placed at place xk. So it means if kth queen can be placed at place xk, if true, what to do? If false, what to do? True means the value is acceptable. So I can easily say I will store this value into my X array. And once I have stored, what next? I have to increment. I have to find the next component. My solution grows incrementally. That will mean nothing but I will call n queen recursively for next queen. And proceed like this. If not, if this was not placed, false. False mean what? False means try next value for xk. Current xk is not acceptable. Effectively means nothing, but just to go back. So I can easily see that if I try to just put my code in a better manner, I will now write it in a more formal manner that I have this code easily ready without much of a problem, where I can easily start saying that for xk equal to 1 to n, if something is correct, if it is acceptable, then I'm going to accept xk equal to this particular variable which I attempted, and then recursively go further. Recursively, I will be having the call here, but recursion is never supposed to be without condition. Recursion has to stop. So where should I stop? And what should be the stopping criteria? So my stopping logic, stopping of recursion has to be there. And that will be obviously when kth queen has, when k equal to n and queen is placed. Obviously, this is going to be my stopping criteria. But if I say in the initial itself, I will check when I wrote void n queen kn. If a first step also, as it is like in normal recursive calls, I write if k equal to n, then I will say stop or non-recursive. Now I can't do that. So that's where backtracking logic versus normal recursive implementation differ. This is incorrect. Why? xk has not been yet found. And it is not guaranteed also whether we will get xk or not. So at this point, initially, I can't decide. Once xk found, only then I can say stop. Once xk has been decided, and now k is equal to n, that is the final answer ready. So with recursion, we have to take care that compared to other recursive implementations, backtracking logic will ensure this at this point. This is the time when I have found the kth answer, and if k equal to n. Not initially. Here I can say, yes, if k equal to n, it means answer is ready. Whether you want to display or whatever you want to display or do, decide. That will be the corresponding condition. Else only, if it is not ready, then only I will have the recursive call. As a recursive call has to be always not with a condition. So the condition will be this, obviously, but not to be placed here. It will be placed here. And having said that, if it is incorrect, if value not acceptable, automatically next xk will be attempted, and so and so. If no value found for xk, no value found for xk will mean if no value for xk, automatically the previous k, that is k minus 1, that recursive call will resume, and the procedure will automatically go. Like from here, n queen 1 will start. This will internally generate call to n queen 2n. That will internally generate call to n queen 3n. And let's say 3n fails. All xk attempted and all xk rejected. Rejected will mean backtrack. And wherever you backtrack, earlier x2 was given some xk. This will be rejected and next xk will be attempted automatically, because I have a loop which ensures this. This loop ensures to resume and next value try. Whenever a backtrack happens, we will be resuming to this loop because there are n calls corresponding to each xk for the next recursion. So it's not only one function. I have all n calls available here. So now what I should write here? So here the bounding function will be used. Let's name that function to be called as a place. So I want my k to be placed at position xk. So I want to write another function, which I will write here slightly, that I want a function place to check whether kth queen can be placed at place xk or not. And obviously, it has to be typing returning int, so that if place is acceptable, true should be returned, because here I have a true value or false value needed. So it will be having int type. Now, what I have to check, whether kth queen is acceptable at place xk or not. How to check? I have to check the attack. Attack of whom? I have to check the attack of all previous queens with the corresponding current queen. What does that mean? That means I have total queens ready up to k minus 1, whether they are attacking or not. So how many queens are ready? Up to k minus 1. So I will check for every queen j equal to 1 to k minus 1. And what I have to check? Whether jth queen attacks the kth queen or not. Kth queen is fixed. J will keep on changing. Where is jth queen placed? What are the coordinates for jth queen? Jth queen is in row number j and column number xj. So this is one queen. The other queen, kth queen, is in column row number k, and possible value of the column number within that kth row is this. So I have to check whether these queens are attacking each other or not. So how to check? First thing is vertical attack. Vertical attack will mean column being same. Column being same means what? xj will be equal to xk. And what about other possibility? So I'll just slightly shift the page so that on the same page we can continue. Yeah. Then I'll say diagonal attack. The other possibility is diagonal attack. So in diagonal, if you say main diagonal, the number of rows if increase from jth queen versus kth queen, the increment in number in rows will be same with increment in number of columns. So like if it was a 2, 3, and this is a 7, 8, they are in attacking position. 2 minus 7, 3 minus 8 is same. Similarly, on the above side, like if this was current queen and I have an attack upwards, so it will mean 7 minus 2 versus 8 minus 3, same. But the reverse diagonal, this side. So rows increase here, but column decreases with the same number, and other side vice versa. So here you have to find out some logic, and you have to think of what should be the possibility of doing. So I will just simply say that if I have to implement my place logic, you have to find out. So I'll say int place was the logic which was I am talking, k and xk being attempted, and I will say for j equal to 1 to k minus 1, if jth queen attacks queen k, then what to do? This means solution is not acceptable. Obviously, I will say return false. Else what? If jth queen doesn't attack, can I return true? No, because only current jth queen has not attacked. All queens must not attack. So if current queen doesn't attack, try next, try next, try next, try next. If you come out of the loop without returning false, probably I can say, now I can return true because no queen attacked. No queen attacks queen k. So I can easily accept the solution now. And something like this. So I think beyond this code, I need not write. I will say or ask you, all of you, to complete the code and understand and finally make the implementation and check it and then find which answers you get. And maybe you can easily think of its time complexity, and from there you will get some clarity that obviously these algos are going to be slower than other techniques because this requires more of exploration, and obviously it will take more time. But for certain situations where you don't have a choice and you are supposed to find all these, obviously this will be needed. With this, let me stop my discussions and